Thank you, everyone. I have a bad cough like 2 or 3 days ago, so please excuse me if I cough during the presentation. Hi, I'm Sai, and I'm assistant professor at New York University. And today I'm present actually for my student Haiyu. He cannot join the ISCA due to the visa issue. And the title is Process Only Where You Look, Hardware and Algorithms Co-Optimizations for Efficient Gaze-Tracked Foveated Rendering in Virtual Reality. So the outline of the talk, so I first give a motivation, followed by some background introduction about foveated rendering. And then I will introduce this POLO. POLO means process only where you look. POLO gaze tracking algorithms and accelerator design. And then I will present the evaluation result and conclude the talk. Needless to say, image rendering is one of the most important applications in the AR/VR field. Basically, you need to process online so that you can continuously render this input image and display in front of the user. And however, this computation is usually pretty costly, and we have to achieve this real-time rendering and to make sure there's no visual experience degradation. Some prior work shows that you have to finish this rendering within this 50 milliseconds threshold in order to let the user to feel the seamless kind of visual experience. However, due to the limited computation capability for the VR devices, this is usually pretty hard to achieve. So to demonstrate this and to motivate this work, so we profile the rendering latencies of different scenes, from very easy scenes to very complicated scenes, and across different resolution. You can see here, like for easy scenes, the latency rendering latencies for one frame is range from like tens or kind of to hundreds milliseconds. And for complicated scenes, it can go up to like 700 milliseconds, which is definitely larger than 50 milliseconds threshold. And to reduce the computation cost for rendering, so foveated rendering is proposed. So the idea is try to leverage the human gaze behavior by only process where the human is looking at. For example, if the user is looking at this red course, so what we can do is, okay, let's just render in this surrounding regions with high resolution, and then progressively reduce the rendering resolutions as the distance getting further away from the gaze location. So by doing that, we can reduce some computations and accelerate the rendering process. But this actually proposes a new question. We have to detect this gaze at real time with pretty high precision. And this is one perfect example to leverage the human gaze behavior to facilitate this rendering application. And there are some other kind of the human gaze behaviors that can also make the rendering cost smaller. One behavior is called saccade. Saccade basically means the duration that the human gaze sweeping from the one location to the other location. And imagine you are looking at one position and you quickly sweep to another position, and this process is called saccade. And the human usually make 1 to 3 saccades eye movement per second, whereas each saccade duration typically range from 20 to 200 milliseconds. And during this duration, during the kind of the occurrence of the saccade, the human visual acuity is actually pretty low. So basically means if we can detect the saccade, we can let the the backend hardware to reduce this rendering cost by doing that in low resolution, because the human cannot detect it based on the prior study. So it seems that we have to, at real time detect the human gaze behavior. We have to detect where the human is looking at, whether there's a cut happen. So is this possible in the VR device? Definitely. So VR device has a lot of different sensors. For example, it has a set of outward facing sensors, try to capture all the kind of the images in front of you and display in front of user. It also has a set of inner sensor, try to censor the human state. For example, it has eye tracking camera, try to continuously take the picture of your eye, and by using that picture, we can actually detect where the human and where the user is looking at continuously. However, this process needs to be done very, very quickly with very low latency. And usually, the modern VR device perform this gaze tracking and rendering all on the GPU. However, GPU runs so many things. You have to run AI applications. It has to run this gaze tracking. It has to run rendering. There are so many workloads this will definitely make GPU can have a pretty high workload and pretty high latency. So because of this case tracking is an always-on application, so we believe it's necessary to design dedicated accelerator to accelerate this gate tracking process. And so what type of gate tracking algorithms we need? First one, it has to be high accurate. Here, for example, on the left-hand side, imagine you're rendering this image with a progressively resolution change and using some gate tracking algorithms. But unfortunately, if the gate tracking algorithms has pretty high gate tracking error, so for example, if the human is looking at this yellow cross, but you are actually render across based on this red cross, so at the end, the user will look at some position which are rendered with low resolution. So this is pretty bad. And one simple solutions to mitigate this is try to enlarge the central foveal regions, as shown in the figure B here. But this, on the other hand, will cause additional rendering cost. So actually, you can see here the accuracy of these gate tracking algorithms is directly proportional, is positively related to the rendering cost. So it's highly necessary to design some gate tracking algorithms with pretty high tracking accuracy. So on the right-hand side, this picture shows a very simple mathematical kind of relations between this gate tracking error and the radius of the central foveal region. So let RF denote the radius of the central foveal region, and the D is the basic distance between the human gaze and the VR display, which is usually to be a fixed value. And the theta I is the angle subtended by the human pupil, which is usually also a fixed number. And the delta theta described the gate tracking error. So the RF is simply equals to D times tangent theta I plus delta theta. So you can see here the smaller delta theta is, the smaller the radius is, and the smaller the central foveal region is, and the smaller the rendering cost is. Okay, so in addition to high accuracy, the gate tracking algorithms itself must also be highly efficient. This is because the gate tracking and the foveated rendering are usually performed in serial. For example, like this, on the right-hand side, we have this latency breakdown. So this shows kind of the rough, very approximate kind of the process to perform each kind of frame for like the gate tracked foveated rendering. So the eye camera will sense the eye pictures and send these pictures to the backend SoC, and the GPU or some other compute unit will take this human eye picture, and perform this gaze detection. And once the gaze detection has been generated, it will forward to the SoC to perform this gaze tracked foveated rendering. So if the gaze detection process itself is pretty long, then the entire process is also pretty long, right? And some profile numbers show that actually the majority of the latency is consumed by gaze detection and rendering plus display. So it's highly necessary to design the gaze tracking algorithms with both high accuracy and low latency. And this motivated our Polo algorithms. So our Polo algorithms will take the input eye image and first try to detect why the saccade is happening. Remember, saccade basically means the human gaze is moving so fast that the human visual acuity is degraded. So if this thing happens, we can already inform the GPU to say, hey, the human is trying to sweeping its gaze, you can render with pretty low resolution because he cannot tell, right? So we simply use a simple, we use the RNN to detect whether saccade is happen. If saccade is happen, we simply render the entire things with low resolution. And if not, then we have to detect whether this human gaze, the human eye image is pretty similar to the last frame, because for most of the time, the human will not move its gaze too frequently. So if there is a highly similar of the human eye image with the last frame, then we can still reuse the gaze prediction of the last frame. So if not, then basically means you are looking at somewhere new, right? So we simply design very efficient algorithms by taking this input eye image and send to a neural network-based algorithms to predict where the human is looking at. But before doing that, because we already knew the human pupil locations, we can simply detect it using some computer vision algorithms. We can crop this input image by put a predefined a bounding box with some predefined width and height, and to only crop the human gaze, only crop the image which are related to the human eyeball, and this will end up with a very smaller, much smaller input, and it will send to the neural network to reduce computations. And in this work, we employ the visual transformer, which has shown to be much more accurate than the CAN, and it basically takes the cropped input image and transfer, send to the self-attention and the FFN block. And during this process, we also apply this token-wise pruning to further remove the less important image patches. The motivation comes from the fact that even we have this cropped version of the input image, there are still some image patches which are actually irrelevant to the human gaze location. So one of the advantage of this gaze tracking, the vision transformer, is you can do this fine-grained prunings by remove this smaller input image patches which are irrelevant to the final result. So by doing this additional level of pruning, we can further accelerate the gaze tracking, the process of this gaze tracking neural network. And the other novelty of this paper is the loss function design. So most of the prior work, they try to train this neural network by minimizing the average gaze tracking error, which is denoted by the summation of theta d and theta d ground truths here. And we have evaluate multiple baselines, and indeed they can achieve much smaller average gaze tracking error. But on the test data set, we observe the gaze tracking error distributions always review a kind of a long tail distribution. Basically means for 5% of the time, the gaze tracking error on this data set is pretty large. So as a user, we do not want this. We do not want this happen, right? We do not want these gaze tracking algorithms only work for 95% of the time. So to mitigate this problem, we simply change this mean average to min max by minimizing the max gaze tracking error and train this neural network. However, there's a lot of machine learning details. If you simply try to min max, then it will result in underutilization of the training data set. So at the end, we did we make this training loss function to be a weighted sum between the mean average and min max to make sure the final neural network has both smaller average gaze tracking error, and also it has pretty good the P95 gaze tracking error. And the Polo network is supported by the Polo Accelerator. And the Polo Accelerator is basically built as a plug-in for the existing VR system. It is in parallel with CPU and GPU. As I mentioned, this because gaze tracking is an always-on applications. So it's highly necessary to have a dedicated hardware accelerator which can run in parallel with GPU to offload some of the workload from the GPU. And the Polo Accelerator consists of two major building blocks. It's the image preprocessing unit. It's try to detect whether saccade is happening and try to perform some CV applications to crop this input image. And the computational engines is implement for efficient implementation for the gaze tracking VIT. And we also have a kind of dynamic token pruning unit, try to dynamically detect the importance of each token based on its attention score and remove it on the fly. And we also optimize in terms of computation pattern. So all I described before is try to describe how do we reduce the total gaze tracking latencies for a single frame. But we can also have some kind of opportunities to parallelize the processing across different frames. So here we show the opportunities, right? So the traditional scheme consists of 4 stages: sensing the eye input image, transfer this eye input image to the backend SoC and perform this gaze detection, GD, and rendering. However, we can pipeline this by make the rendering of the last frame happen in parallel with the sensing of the next frame. And in addition to that, we also noticed that this foveated rendering can also be performed in a hierarchical fashion. So imagine, for example, if you are looking at this dark brown region. And what you can do is you can perform this foveated rendering in a hierarchical fashion, so that in the first round, you can render the entire image with this low resolution by only render this light yellow pixel. And in the next round, once you get the precise gaze location, you can render the missing pixel in the middle. So what does this mean? This basically means you can break this foveated rendering into 2 stages, where the first stage, called R1, does not need the precise gaze tracking location at all. So you can parallelize this with the gaze detection module. And once gaze detection is finished, you can use this as information to perform this hierarchical rendering, which is shown in R2 here. So this new computation pattern further reduced the total latency of the gaze tracked foveated rendering. And finally, we describe some evaluation result. So this is the accuracy evaluation result. We compare this Apollo VIT against some prior work here. And we evaluate Apollo under different token-wise tuning ratio, from no token-wise tuning, 0.0 to 20% to 40%. We show that our Apollo VIT can achieve the lowest gaze tracking error and the lowest P95 percentile error. And we simulate this Apollo accelerator using Synopsys DC. And we also simulate this GPU in the VR device using Vulkan Sim. And we can estimate the entire latencies per frame latencies for this gaze tracked foveated rendering. And we evaluate that on different scenes and different resolution. We can show that the Apollo reduced the latency by up to 4 times in the most complex scenes, with an average reduction of 2.5 times at 1080p. And finally, to investigate the impact of Apollo on the real user visual experience, we artificially inject this Apollo processing latencies to the gaze tracking module on the Meta Quest Pro. And we also implement this foveated rendering on Meta Quest Pro, and we compare our Apollo solutions with the baseline. Baseline basically means render the entire image with full resolution. We can show that within the 7 users, most of the users prefer the visual experience provided by Apollo rather than baseline, because the baseline rendered too slow. And in conclusion, Apollo brings a new insight on human gaze behavior to facilitate the process of gaze tracked foveated rendering, and highly efficient neural network-based gaze tracked solutions is described, and hardware plug-in is introduced to the existing VR platform. And with this, I'd like to thank you for your listening, and I'd like to take questions you have. Thanks.